Hi everyone. So today we are going to look at my project that we have done is on linear regression using the PyTorch C API, that's the front-end API. And the Facebook guys have been working on this for quite a long period of time to try and make it as close as to what we have in Python for PyTorch. And so all credits to them for making this as close to as what we have in Python. And I hope this is useful for those who are trying to use deep learning in C++, trying to get as close as to production environment as possible. So let's go ahead and look at this project. So the target of this project was not to get the best accuracy possible, but to try and make it possible for users to use custom CSV files for regression tasks in C++. Okay, so we're not going to focus on whether we get the best accuracy, whether we get the least loss possible for any kind of linear regression task. That is not in the umbrella of the task that we have. So this is the linear regression using PyTorch C++ API. You can see on the screen we have a good self-explanatory README for those who want to just go ahead and run this project and see how it goes. So you can just go ahead and look at the usage. What I'm going to do is we're going to first look at the usage. We're going to run the project. We're going to build this project first, then execute the binary file and see what output it gives. Once we are done with this, we're going to look at the source code and I'm going to explain what kind of design patterns I'm going to follow in all these projects that I've been doing, and hopefully this will be clearer for you guys if you want to contribute to this project. I totally appreciate that. You can just go ahead to the issues section, and if you see an issue open or if you want to open an issue, you can go ahead and do that. So let's go ahead and start looking at this project. First of all, the first and foremost task is to clone this repository to your local system. Once you have done that, what we're going to do is we're going to look at the source file, we're going to look at the include header files and all those things, but we're going to configure our project first. So if you're new to CMake configuration thing, maybe after this video you can just go ahead and scroll through a tutorial on CMake configuration. I can provide some useful links in the description. So please go ahead and do that. It's quite useful nowadays for production environments. So let's start, and what I'm going to do is I just did list files in this directory, and you can see we have src, which contains all the source files that we are going to use. We have include directory, which includes all the header files that we have. So this is a typical conventional workflow of any C++ project that we follow. So let's go ahead and do this. I'm gonna make a build directory, and this is just to make sure that we don't have a lot of noise in our main directory, and whatever CMake configuration does, it does to our build directory and not the main directory. Okay, so I'm gonna do this. I'm just gonna clear this out. So right now this directory is empty. Let's start with first I'm gonna configure my project. So for this I'm gonna use this CMake prefix path. What it does is, I'll explain once we are done with this. So if you see, what it's trying to do is trying to find what are the available compilers, what are the available libraries that need to be linked to, and we have provided the CMake prefix path to our Libtorch folder that we downloaded from the pytorch.org website, and we're gonna use that because our C++ file has a dependency of Libtorch, obviously. So all it does is, you can see that it finds torch for you here in the folder I provided. It configures our project, it generates the make files, and if you're interested, you can just take a look at the CMake cache.txt file that is generated, and you will see it has a lot of paths to libraries, and these are just for the understanding for when we're going to build this project. It will take all these libraries, it will find those libraries in these folders and so on. So if I do ls, you'll see there's a make file in this directory, and that's why we have a build directory separately, so that our main folder is not crowded with all these files. So I'm going to just clear this out, and if I do a make command, now it's kind of equivalent to what we would do normally in C++. If you're using G++ compiler, you will just do G++ in file name .cpp, right? Now here I'm going to do is I'm going to make this project, So I'm going to build all my make files, and once I'm done, I can just go ahead and execute my binary files that have been produced. So you will see it has built the target LR example. It is in bin slash LR example. So if I have to run this project, I can just do this dot slash bin dot slash dot slash bin slash LR example. And you will see the loss, it prints the loss for all the epochs that we have. I have around 100 epochs. So you can see the loss, the mean squared loss that I'm using is 590 initially for the first epoch, and for the 100th epoch I have 82.6705, and it's kind of converging to the end, and which is good. So it means that our network is learning, it means that our network is working fine, and you could always go ahead and print the outputs, you could always compare how it goes and all those things, you could do that. So let's go ahead and look what's happening in the backend now, because for some of you, you might just want to look at, was it that trivial as it sounds, or what went into this development, right? So I always do this thing that whenever I have a new project in mind, I just go ahead and look at the main file that I have. Okay, so all I'm going to show you right now is this regression.cpp is kind of the main file that runs, and we're not going to look at all the header files. We're not going to look at all the helper functions. Right now, we're just going to focus on the main function, right? So step by step we'll go. Whenever we find there's a function that we don't know about, we will take a note of it and we will discuss it after we have done with this file. Okay, so we're gonna go step by step. So for any deep learning project, if you are familiar, you will know the first phase is to load the data and process it for our task. Now this is kind of process, whatever process you're going to do for the data is kind of task specific, and it depends what task you are on. For here we are going to do linear regression, so we're going to use normalized features and all those things. If you're doing something else, you might just want to do use different kind of normalization or anything else. So let's go ahead and see how we are going to do this. The aim was to be able to load CSV data. So the first thing is we're going to load our CSV data. We are using ifstream library for all these things, and all it does is it takes the path, and we just open this file, and if it's not open properly, we just return this error, which is kind of good. You don't want to have a segmentation fault later on and you realize, oh, the file path was not right. Okay, so this is something we always do. And if you notice here, what I'm trying to do is, if a user has provided a command line argument to his or her custom CSV file, then the program should be able to use that instead of what we have in the extras folder. So all it does is, if argument count is greater than 1, then use argv1, or if it's not greater than 1, that means there's no command line argument to this, then we just use the default /extras post and housing.csv file. This assumes you're trying to run in the build folder. That's why we have // okay. So this is done. All we're trying to do is we're trying to open the file. Once we have opened this file, if you notice, I'm going to call this process data function, which takes two arguments. One is the file that we have opened, okay, and the other thing is row. If you see this row, I've declared it here, right? And this is the object that we have created, and we will discuss about this later on. But all we are trying to do is we're trying to read row by row of the CSV file, and just as we go row by row, we kind of save all the features to our 2D arrays and labels to 1D array, and finally give this output where we have this pair of 1D arrays. One is for feature, one is for labels. So for now, let's just assume all this process data function does is it processes the data, it loads the features and labels for linear regression task. Okay, it whatever it be, like, just don't think about it what it does. Okay, just know this, that it returns 1D array for feature, 1D array for labels. That is it. So we'll take a look later on when we go to the include files and discuss about this class. So the C++ has a very cool thing, because we cannot use tuples in C++. We cannot return multiple arguments like the way we do in Python. So we have pair. what we how we you know how we use the first argument of this pair. The first parameter of this pair is out.first and the second is out.second. So out.first are the inputs and out.second is the outputs of our data. So you can just call inputs as features and outputs as labels depending on whatever you want. So we're kind of done with data creation. We have loaded the data, we have processed the data. All we need to do right now is convert them to our PyTorch tensors, because it's kind of useful and it's kind of necessary as well when we are passing these features and labels to our network. These need to be in torch tensor data type, right? These, sorry, not data type, these should be of torch tensor types. So all I'm going to do is I'm going to use this function from torch namespace called from blob. All it does is it takes the data from our vector. And so how do we get the data from our vector? We do outputs.data. Okay, that returns the data of our in our vector. And all it does is it resizes this to this shape, the shape that we are given here, int outputs.size comma 1. So if I have to hard code you, and that will be easier for you to understand here. So in our CSV file we have 506 samples. So output tensors, now it should be of size of 506 comma 1, right? Because we have 506 samples and we only have one label per for each label, because we have just one label. That's why 506 comma 1. And for input tensors, this should be a 2D array, right? Because we have uh, in this data set we have 13 features and we have 506 samples. So this is something we have already for input tensors. And we don't want to hard code it. That's why what I've done is outputs.size will return 506 and 1 will, because we're doing linear regression, it's kind of obvious that we only have one label. So if you're going to do multiple linear regression or something like that, you can just increase this count by something else, 2 or 3. And for our inputs, what we're going to do is, again, outputs.size will return 506. And to calculate the number of features, all I'm going to do is, so what the thing is, inputs.size here will be, since it's flattened, that we'll discuss later, but here it is actually 506 into 13, and we have outputs.size as 506. So I have this as 13, right? So this gives me, let me just do, yeah. So once we have inputs.size as 506 into 13, we then divide it by outputs.size, and then we get number of features as 13. So here I'm trying to resize my inputs to something like, so input tensors should be of size of 506 comma 13 here. So that's how we're going to do this. And now after this step we have output tensors of size 506 comma 1, input tensors of size 506 comma 13. So once we're done with this, the next step is to create our network, right? So uh, again, you won't see the network configuration here. That is in the header files. That is how we try to keep things simple. Here in the main function, all I'm trying to do is I'm allocating all the space. I'm initializing my network with input dimension of, so here the input dimension is what? So you see input tensors dot sizes, and I'm accessing the second index, that is 1, because we start with 0, right? So here it's going to be 13. If you see here, right, 506 comma 13. So this one is going to return 13, and the output dimension is to the network is going to be 1. So this is because the input dimension we have are number of features. That's what we're going to do. And for our number of labels we have 1, so the output dimension should be 1, right? So this is how it's going to be. And so once we're done with this, let's go ahead and look at what do we have. We have the optimizer. We are going to use SGD, the stochastic gradient descent. If you're keen to look at how it works and all those things, it's not in the scope of this video, so you can go ahead and look at any tutorial you wish. Here I'm trying to pass learning rate as 0.001. Please know that if the learning rate is not small enough, like 0.001, it might just not converge. It might give you infinite loss later on. So it's linear regression is this learning rate is something that you should really tweak according to your project, according to your data set, and according to your network configuration. So just take a look at what works for you and use that. I'm using 0.001. It works fine for me. Okay. So once I have the network, I have the data set, all I'm going to do is going to train my network and I'm going to print the loss. So it's kind of really same like we do in Python. We have number of epochs as 100, and I do a forward pass for all the input tensors here to our network. I get the output, and then I calculate the loss between the output and the output tensors. That was the real labels, right? And then I convert this loss into floating point, because this again this torch MSE loss returns a tensor, and to get the floating point value from this tensor, I I use this loss.item, and we convert this into flat float. So once we have the loss value, we just print this out, and that is done. So this loss dot backward optimizer dot step are typical training functions that we use. So we're trying to do is we are updating the gradients. We are moving forward with our SDD process. We are moving step by step, and we are backpropagating our loss for the learning purpose, right? So this is it for the main function. Again, there were three phases. First, we created our data, right? We loaded our CSV file, we processed the data, we got the output and input in form of PyTorch tensors, and once we have that, we create the network and then we train and print the loss. So this is it for our main file, what we are trying to do. What about this process data function that we used and the network configuration, how we did? Okay, so these are included in our header files. Okay, and we're going to look at them, how these functions work. And if you're eager to look at the source code, if you're one of those guys like me who like looking at the source code and trying to figure out a way to contribute to these things, so this is the right time for you to look at the header files that we have, right? So if I see, we have include folder, right? So before we take at the CSV load, before we take a look at the CSV loader.h file, that is the header file that contains all the definitions for our class for loading CSV file. Let's take a look at the CSV file, the format of it. So if you see, the format is the first row we have are the name of the features, and after that all we have is the values corresponding to each feature. In total, if you see, I have 506 samples, okay, and for all these things, all these are the features, right? And the last column is the label of this data set, okay? So this is the typical format of any CSV file. These are comma separated rows. So that's what we're going to do. And let's take a look at the CSV loader.h file and try to understand how it works. So again, this is whatever code I have inherited from any other website. I have given due credits, and that's what you should do as well. And so this is one of the classes I found which were kind of neat and easy to understand. And for the scope of this project, this kind of does everything for me. So I don't have to worry about loading a CSV file in C++. Okay, but for PyTorch it's different. So for C++ it works fine, right? So I've given due credits in the README file. You can go ahead and look at the user profile and thank him for that. Okay, so right now we have class CSV row, and if you're familiar with C++, you're gonna look at this float operator here. All we're trying to do is we are doing operator overloading. That means if I have a object of this class CSV row, and if I do this row of 0 after I've read the files, then this is going to return me the value of in the row at 0th index. Okay, so all it does is for the row that we have read, it returns 0th feature value, right? So this is what it does. So this is why we call it operator overloading, and all it does is it takes the value in the data in that index as a string format, and it converts that into floating point value, right? Because sometimes in the CSV file, like in our file, you can have values similar to this, even though it's integer or it's float, but it's still in a format of string. So we need to make sure that it's converted to floating points, right? Because all these operations are done in floating point floating point variables. So again, this is something which will be very useful. If I do row.size, it returns the number of features, that is, it returns the length of the row that we have, and it's kind of useful when we want to, use this in the for loops and all those things. So this is kind of useful. And read next row is something we should not look at right now. We don't need to, but all it does is reads the line, it splits according to comma, okay, and it pushes this value to cell, and that is it. It pushes it back to m underscore data variable. That is a vector we have, and that is it. So there's another operator overloading here for this operator. All it does is it takes, so we are using this if stream. uh, Remember earlier we used standard if stream file path, and we provided the path to our CSV file here. So all we are doing here is we're loading the file to our row one by one, right? And once we have done that, every time it returns a row into this row object, and we can access the first row in our first iteration. Okay, when we go to the second iteration, we have the second row, and so on. So we have 506 rows. So in the last iteration, you will have 506th row. And once that is done, so while loop is automatically, we come out of this loop, because while file this operator and then row, this will turn out to be false because it's empty, and that is it. So this is it for CSV row header file. Again, this is not something that you should take a deeper look into if you want to look at PyTorch C++ API and all those things. But if you're eager how this is done, and if you want to do some tweaks with it, please feel free to do that, and it should work. So then we have utils.h file. This is the header file for our utility functions. This is something we always do, that we keep our functions in, defined and declared in header files. So I'm not, follow the best convention that we do. In header files, you will usually see only declarations, and in the source files, you will see the definitions. But for now, I've kept all the definitions in this header file. This might change in the next release. For now, this is how it looks like. So if you remember from our last discussion, we had used this process data function. So we have this process data function here. All it takes is the file and the CSV row object. So this, I've added this comment for the ease of understanding. This function processes data, loads CSV file to vectors, and normalizes features to 0, 1, assumes last column to be a label and first row to be a header or name of the features. So you will see why all these assumptions have been taken. So as I told you before, this operator was overloaded. Now we have, when I use while file and this operator in row, it stores the first row into this row object, and then I have if count equal to 0. That means if I'm in the first row, just continue, just skip all the code that is in this loop and just go to the next iteration. This is because I don't want to read the first row, that is the name of the features. That's not useful for me, so I'm not going to read that. So if your CSV file does not have the first row as the name of the features, you can just skip that. If that's not the case, if you can, if your first row is not the header row, you can just delete this if condition or just commit it out. And for the next iterations, all we have is we iterate through for int I equal to 0, I less than row.size minus 1. Now, as I told you before, this row.size function will be very useful. Initially, when we have read the row, the row.size is equal to 14. So it also includes the label column, right? It also includes the label value. That's why we have 14 as a row.size. And since we only need to read the features in this for loop, so that's why I'm using row.size minus 1. So all it does is it skips the last column, it skips the last value, sorry, and that's what we have here. again, if we are in the first iteration, we want to make sure that we have initialized this our 2D feature vector. It's initialized, if you see, it's declared here. So it's kind of a 2D vector because our data set is in this form, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's say if we have 3 features, okay, and we have 3 rows. So it will initially be a matrix of dimension 3 cross 3. So for our project, the dimension will be 506 cross 13 because we have 506 rows and 13 features. So initially when this features is declared, it's like this. So I can't do this in C++ because the memory has not been allocated. So when I'm in the first iteration of this, I need to make sure that I just push a vector to each index like this. So when I've read the first file, when I've read the first row, what I've done is first I pushed 1 as a whole vector, then 2 as a whole vector, 3 as a whole vector. Then in the later stages, I can just do features 0 dot pushback, let's say 4, right? Sorry, 4. So what it does is it pushes, this is what it does. So now this becomes 1, 4. So this is how we are going forward by this approach. This of course can be changed if you know something else that can be done. Just file an issue and make a PR out of it and let me know. So this is what we're trying to do. If we are not in the first iteration, all we do is features I.pushback row of I. Okay. So here we are trying to make a feature. We are initializing the feature 2D matrix with all the values, and of course push the final column to label vector. The final column will be row.size -1, of course. So that is it. Our loading data into features and label is done. Once we have done that, for deep learning, for linear regression here as well, we prefer normalizing, and it's usually the case where we normalize to 0, 1. This can be changed depending on the data set you are using. You can use some other metric, you can use some other kind of normalization, but here we are using simple normalization 0 to 0, 1. So we don't need to normalize our labels, okay? We are just going to normalize our features. Now here we are going to normalize features, and for int I equal to 0, I less than features dot size and I plus plus, that all it does is for I in features, and we just normalize features and with I. So this is it. That's all it does. But so this is in Python. Okay, if you're familiar with Python, I just thought that I'll convert this into Python and I'll explain how it goes. So this is pretty simple. All it does is normalizes features. Then we have, so what we do is we don't want it to return feature vector as 2D, because later on we are anyways converting this whole 1D vector into 2D vector, right? Using torch from blob function. So what we do is we flatten this vector, and it's kind of equivalent to this. First we initialize a new vector, 1D vector, with features of 0. That means the first feature vector we had in our 2D vector, right? Initially, if you remember, our matrix looked like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, and our features would look, essentially it will look like this: 1, 4, 7 and 2, 5, 8 and 3, 6, 9. Right. So all I'm gonna do is I'm gonna initialize this with features of 0. Right. Sorry. And so I'll reserve the size for this 1D vector so that I don't waste all the memory. So that's all I'm going to do is inputs.reserve total, and total is the sum of all the sizes taken by this feature vector. Here in this example it's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. These are total 9 elements, but for our data set is 506 and 13. Okay, and all I'm going to do is I'm going to do inputs.insert. That all it does is I now have 147, 258, 369. So I've converted this 2D vector into 1D vector, and that is it. So we are done. That was a requirement. We wanted to return 1D vector of features. We wanted to return 1D vector of labels, and that's something we have done. So we want to return these arguments in C++, how do you return multiple number of arguments? We just use make pair, and we make pair of inputs and label, and we return that. That is it. So in all this thing, we have used normalized features function as well, and we're just going to take a quick look at this. So the formula we're using is x minus min divided by max minus min. So all we are trying to do is we first find the max element, then we find the min element of the feature, and then we normalize based on feature of I minus min element divided by max minus min. Do remember that sometimes it can be the case that all the values are 0 in a feature vector. I don't know if you want to keep that feature or not. It's totally up to you. So all we need to do is max minus min plus 1, so that you don't get the you don't get this divide by 0 error, or you don't get infinite values or nan. So that's something you should take care of. So let's take a look at this network definition here. It's kind of small. I have not used any activation function. You can always do that. So all it has are dense layers. Dense layers, that means fully connected layers, and that is it. So um, you can use this network definition as I've provided a comment here. std make sure net is just a template type that we pass for make shared function. Okay, and this is input dimension 1 and output dimension is 1. So that's just one example. Here we had 13 comma 1, right? So we have initially we have 13 neurons, then we pass on all these values to 500 neurons, then we have 500 to 500, then we have 500 to 200, and then we have 200 to output dimension, that is 1. So this is how a fully connected layer usually looks like, and you don't need to understand how this works. It's quite simple. We have a forward function which does forward pass to the data, and that's why we have x is equal to fc1 forward 2, and we pass x to it, and so on and so forth, and we return x. So that is it, and just make sure that you initialize all these layers with null pointers, and later on we obviously when we are registering the module fc1 to this linear layer, then we allocate all the memory and all for it. Okay, so that is it for the code part of things. I know it can be tough for you to understand, and I'm sorry if I was too fast, but this is how the project looks like, and you can always go ahead and contribute to these projects. It's not that hard for you to understand. Sorry, so I just loaded a lot of files. So this is it for this video. Again, all we tried to do was use a CSV file, try to train it for linear regression task using PyTorch C Frontend API, and that was it. If you are keen to understand, just take a look at what went into this project. You can just go ahead and look at the PRs that we have done. So I've tried to manage a lot of things. We always try to make sure that we have documented all the changes that we do. So for example, if I go to this major release that we had, so you can just go ahead and look at all these commits that we have done. We had an issue for it. We were tracking all these changes, and at times we felt, that something was not useful. We replaced that with another thing, and all those things. Okay, so we do appreciate if you take a look at all these projects and want to contribute. That's always welcome. If you see an issue with open source label in our Buffet Codes organization, just go ahead and let us know that you want to work on it, and we can discuss it forward. So for those issues which we think that we can better solve it ourselves, and maybe it requires some contextual information or contextual knowledge about the project, so we just take it on upon ourselves to solve that issue. But if you feel like, okay, this still can be done by me, just let us know. Okay, we are always welcome for discussions, and that is it. So for the next time, I'll be discussing me or my teammate. If you want to have a look at this organization, just take a look. Me and Himanshu Singh are working on these projects, and just we'll be back with another video on one of these projects and try to show how you can actually build these things. Also, one last thing, I'm using Windows subsystem for Linux here. I'm not using Windows. WSL2 I'm using, and it ships with Linux kernel, which is kind of good. And if we are this all has been tested on Windows as well, okay? And if you want to go ahead and do it on Windows, just to use Visual Studio for that, or any kind of tool that you use. I wish you luck for that. And that is it. So let me know how did you like this video, and I hope to see you guys around. Bye bye.